Welcome to this practice stop. In this exercise, we will perform a finite difference approximation of the first derivative. We will use a Casio FX991ES Plus to obtain the required function values and then calculate the three finite difference estimates. Here is the practice problem. We need to estimate the first derivative at x equals 0.25 using a step size h of 0.25. Our function is a fourth-order polynomial. Our goal is to compute three approximations and compare them with the exact derivative. Hint: calculate the three function values first, as they are the inputs for all three formulas. Let's review the finite difference formulas. Forward difference uses the point to the right of x, which means f of 0.5 and f of 0.25. Backward difference uses the point to the left of x, meaning f of 0.25 and f of 0. Center difference uses points on both sides of x, meaning f of 0.5 and f of 0, and divides by 2h. To generate these function values quickly, we can use the table mode on our Casio calculator. Let's watch a demonstration of how to enter the function and set the start, end, and step values to generate our table. In this demonstration, we will use table mode to obtain the function values required for our finite difference calculations. From the calculator's main menu, press 7 to select table mode. Now enter the function exactly as shown in the practice problem. Negative 0.1 x to the fourth minus 0.15 x cubed minus 0.5 x squared minus 0.25 x plus 1.2. To enter the variable x on the FX991ES Plus, press alpha, then the close parentheses key. When the calculator asks for a second function, g of x, simply press equals to skip it. Next, set the table parameters. For start, enter 0. For end, enter 0.5. For step, enter 0.25. The calculator now displays the values we need. At x equals 0, f of x is 1.2. At x equals 0.25, f of x is 1.1035155625. At x equals 0.5, f of x is 0.925. Record these three values carefully. They will be used immediately in the forward, backward, and centered finite difference formulas. As we saw in the demonstration, the table mode produces these results. At x equals 0, the function value is 1.2. At x equals 0.25, it is 1.1035155625. At x equals 0.5, it is 0.925. These three values are all we need to calculate our estimates. First, the forward difference. We use the formula f of x plus h minus f of x, all divided by h. Plugging in our values, we subtract 1.1035155625 from 0.925 and divide by 0.25. This gives a forward difference estimate of negative 0.7141. Next, the backward difference. We use the formula f of x minus f of x minus h, all divided by h. Plugging in our values, we subtract 1.2 from 1.1035155625 and divide by 0.25. This gives a backward difference estimate of negative 0.3859. Finally, the center difference. We use the formula f of x plus h minus f of x minus h, all divided by 2h. We subtract 1.2 from 0.925 and divide by 0.5. This gives a center difference estimate of exactly negative 0.5500. Now, let's check against the exact derivative. Taking the analytical derivative of our polynomial and plugging in x equals 0.25 gives an exact value of negative 0.534375. Calculating the absolute error for each method, we find the forward error is roughly 0.179, the backward error is roughly 0.148, and the centered error is roughly 0.015. Looking at the final comparison table, all three methods estimate the same derivative, but with very different accuracy. The key takeaway here is that the center difference is closest to the exact derivative for this example, which is consistent with its higher order accuracy. Before you go, here is an exam memory aid. Forward looks to the right, backward looks to the left, and centered uses both sides. Your workflow should always be: get your function values, choose the formula, substitute, calculate, and compare the error. Good luck on your practice.